Welcome back to AI.Code.Cast. You know how we do it diving into a fresh coding challenge every single day.
That's right.
And today, we're tackling something that feels a bit like those sliding tile puzzles, you know?
I think I know where this is going.
You've got these strings with L's, R's, and a bunch of underscores thrown in for good measure.
The L's, they can only slide left. The R's are stuck going right.
Exactly. And the underscores, think of them as the blank spaces where all the action happens.
But there's a twist, right? It's not just about sliding things around aimlessly.
Oh, absolutely. You're given this target string, the final arrangement you're trying to reach.
And the big question is, can you actually rearrange that original string to match the target while sticking to those pesky movement rules?
It's tougher than it sounds, trust me, to really wrap our heads around it.
Yeah, let's grab an example.
Perfect. Let's pull up example 1 from today's source material.
Okay, sounds good.
We're trying to figure out if we can transform LRR into LRR.
All right, so how would you even start with something like this?
Me? I'd probably just jump right in and start shifting those L's and R's around, see what sticks.
It's tempting, I get it.
It's that brute force instinct, right?
Huh.
Just try everything until something works.
That's exactly what we call it, a brute force approach.
Systematically try every possible combination, no matter how long it takes.
The problem is, well, imagine a string with even more characters.
Uh-oh, I see where this is going.
The number of possible arrangements just explodes.
Talk about a headache.
You're essentially trying to solve this massive jigsaw puzzle, but you're just randomly moving pieces around.
Hoping to get lucky and stumble onto the solution.
Exactly. It's like searching for a needle in a haystack, but the haystack keeps getting bigger and bigger.
So brute force might work for, like, super short strings.
Maybe, if you're lucky.
But as that string gets longer, forget about it.
It becomes a computational nightmare.
You're telling me. And then there's the whole memory issue, right?
Oh, absolutely. You're likely to hit that dreaded memory limit exceeded error.
Oof, I've seen that one too many times.
Your computer's just like, nope, can't handle all these possibilities.
It's like trying to stuff an ocean into a teacup, isn't it?
The perfect analogy. Too much data, not enough space.
So if brute force is off the table, what's the smarter way to tackle this?
Yeah.
There has to be a more elegant solution, right?
There absolutely is, and it all comes down to really understanding those movement restrictions.
The L's and R's, they're trapped by those underscores. They can't just leapfrog over each other.
Exactly. It's not just about finding any arrangement that matches the target. It's about figuring out if you can even get there, given those rules.
You have to follow the traffic laws of the string world.
That's a great way to put it.
Okay, I'm starting to see the bigger picture here, but this all feels very abstract.
Let's make it a bit more concrete.
Perfect, because my brain is definitely craving some visuals right now.
Think of it like cars on a single-lane road, no passing allowed.
Okay, I'm listening.
The L cars, they can only go forward.
Right, like they're in the fast lane, no backing up.
Exactly. And the R cars, well, they're stuck in reverse.
Always backing up. That sounds a bit chaotic.
But here's the thing, the order those cars start in,
That initial arrangement.
it dictates which final arrangements are even remotely possible.
So if an L car needs to end up before an R car in the final arrangement,
Yeah.
but it starts behind that R car, well, there's just no way to make that happen.
Precisely, they're stuck in their lanes.
That analogy really clicks. It's like a string-based traffic jam.
And it leads us to a much, much more efficient solution. The two-pointer method.
Two-pointer method. Okay, now you've got my attention. What's the gist of it?
Imagine you've got these two pointers, like little arrows, one on the original string, the other on the target string.
I can picture that.
You move them simultaneously, comparing the characters at those pointer positions.
And checking if those moves are even legal, according to our L and R rules.
You've got it.
Okay, this is intriguing, but what about those underscores? Do they play a role in this two-pointer dance?
Excellent question. Because that's where a lot of people trip up. Those underscores, they're like empty spaces, right?
Yeah, just blank spots on our string highway.
So we can skip over them as we move our pointers.
So we're not just comparing characters at the same index in both strings.
Nope, not blindly.
We're strategically moving those pointers, taking those empty spaces into account.
Exactly, and that's a key efficiency boost right there.
I'm starting to see the light, but some concrete examples would really solidify this two-pointer concept.
Let's do it. Let's walk through a few examples from the source material. I think you'll be amazed how much simpler this is compared to that brute force nightmare we talked about earlier.
Lead the way.
All right.
Okay, let's get down to business with these examples.
All right, so back to example 1.
That LRR to LRR transformation.
Right. And remember those 2 pointers we talked about, our
Mhm.
trusty little arrows?
Oh yeah, they're ready to roll.
They both start at the very beginning of their respective strings.
So pointer 1 is looking at an underscore, and pointer 2 is fixated on an L.
Right on. Now what happens next?
Well, those underscores are like empty spaces, right?
Exactly.
So we just slide right past them.
We do.
Okay, so pointer 1, the one working on the original string, it keeps moving until it hits that L.
It does, while pointer 2 patiently waits on that L in the target string.
So they're both synced up, both staring at an L.
Now we've got to make sure a few things check out.
Like what?
First, do the characters actually match? Which they do here, both are L's.
They do. What else?
Then we check if the position of that L in the original string can legally lead to its position in the target.
The movement rules.
Right. So let me see. The L in the original string, it's at index 1.
And in the target string, it's at index 0.
And remember, L can only move left.
So to get from index 1 to index 0, it'd have to move right. Illegal move.
Busted. That L can't get to where it needs to be.
But wait, does that mean the whole transformation fails?
Not necessarily. Remember, we're checking each L and R individually.
Right. So we just keep moving these as pointers.
Exactly. Let's see what happens.
Skipping over more underscores. Pointer 1 lands on the R at index 4.
Okay.
And pointer 2, it's at the L at index 1.
What do you notice there?
The characters don't even match.
Exactly. We hit a roadblock. This whole transformation is impossible.
And we can just stop right there.
We can. No need to go through the entire string.
That two-pointer method, it's like a shortcut detective finding the culprit early.
It's all about those early exits. Saves us a ton of time.
Okay, let's try another one. What about example 2 from our source material?
Sure. That one's R to R.
All right, pointers start at index 0, both staring at those underscores.
Right.
Skip ahead, and now they're both looking at the R.
Perfect. Pointer 1 at index 1, pointer 2 at index 0, both on the R. What do you think?
Well, the R, the original string, it's to the right of the R in the target.
Yeah.
R can only move right, so moving left to get to index 0, that's totally legal.
Boom. Perfect analysis.
Like it just slid into that empty space.
And R pointers, they've reached the end of their strings.
And all our checks passed along the way.
Which means
This transformation, it's a go. We can make it happen.
we can.
This two-pointer method, it's really growing on me.
It's elegant, isn't it?
Those pointers just glide through the strings, no fuss, no muss,
We're like little dancers.
skipping over those empty spaces, making sure everything lines up perfectly.
And so much more efficient than that brute force approach.
You know what's really cool? It feels like we could use this for more than just L's and R's.
Oh, absolutely. This is just the tip of the iceberg.
The two-pointer method is like a universal tool.
Exactly. Whenever you're dealing with sequences of data strings, arrays, you name it.
And you need to compare things or look for patterns, the two-pointer method can swoop in and save the day.
It's like having a Swiss Army knife in your coding toolkit.
That's a great way to put it.
Yeah.
But are there any, traps we should watch out for with this method?
Of course, there are always things to keep in mind.
What are some common mistakes people make?
The biggest one.
Yeah.
Forgetting about those underscores.
Oh, right, those empty spaces.
People get tempted to just compare characters at the same index in both strings.
But that wouldn't work, would it?
Not at all. Those underscores, they're crucial for movement. They let those L and R cars switch lanes.
If we ignore them, we miss the whole point of the sliding around.
Exactly.
What else? Any other pitfalls?
Well, sometimes people mess up the position checks for the L and R movements.
The less than, greater than stuff.
Yeah, it's easy to get those mixed up when you're figuring out if a move is valid.
I can see how that would happen to many symbols. Not enough coffee.
It happens to the best of us.
So it's really important to remember that car analogy.
Always visualize those L cars moving forward, the R cars backing up.
Makes those constraints much clearer.
Exactly. A solid grasp of the problem is key.
Okay, so we've covered the pitfalls of brute force, explored the magic of the two-pointer method.
And even pointed out some common mistakes to avoid.
I'm feeling way more confident about tackling these kinds of problems now.
That's what we like to hear.
Speaking of confidence boosts, any final thoughts about the two-pointer method?
Well, the real beauty of it is its adaptability.
We've been talking about L's and R's, but it goes beyond that, right?
Way beyond. This core idea using two pointers to efficiently compare data, it pops up everywhere.
It's a tool with a lot of potential.
Absolutely.
So we got the mechanics, the pitfalls, the big picture. Anything else before we wrap up?
I'd like to leave our listeners with a challenge.
Ooh, I love a good challenge.
How would you adapt this two-pointer technique for even trickier scenarios?
Like what?
What if, instead of just L and R movements, we threw in a third element?
Interesting.
Let's say a B that can move in either direction.
Whoa, that changes things.
How would you tweak the two-pointer approach to handle that?
That's a good one. Really makes you think.
It's all about pushing the boundaries of what you know, right?
Taking that basic concept and turning it up a notch.
Exactly. It's all about that creative spark, the exploration.
That's what makes coding so exciting.
And that's what makes AI.Code.Cast so much fun, wouldn't you say?
Yeah, a bidirectional element. That throws a real wrench in our plans.
It does, doesn't it? But that's what makes it interesting.
It does. It's like we have to rethink the whole system.
Exactly. It challenges you to really understand that core logic of the two-pointer method.
Not just applying it blindly, but adapting it.
Right. Like, how do we modify it to handle this new, trickier situation?
It's like we're upgrading our coding toolbox.
I like that analogy.
Taking a familiar tool, but figuring out how to customize it.
For a brand new problem.
Exactly. It's like the creative side of coding really shines here, don't you think?
I agree. It reminds us that coding isn't just about memorizing algorithms.
It's about truly understanding those fundamental concepts.
And then using your ingenuity to apply them in new and exciting ways.
It's like solving a puzzle, but you get to make up the rules as you go along.
Exactly. And that's what we try to capture here on AI.Code.Cast.
Yeah, that spirit of exploration.
We're not just giving out answers, we're inviting everyone to join us on this coding adventure.
Who knows, maybe one of our listeners will crack that bidirectional element challenge.
We'd love to see some creative solutions out there.
Definitely. Always encouraging our listeners to share their insights.
Because that's how we all learn best, right?
Absolutely. By sharing and learning from each other.
I couldn't agree more.
So let's wrap up today's deep dive into rearranging those L's and R's.
What are our key takeaways?
We learned that sometimes the most obvious approach, like brute force, isn't always the best way.
Especially when those problems can spiral out of control in terms of complexity.
It's like trying to fit an elephant in a refrigerator. It's just not going to work.
But we discovered this elegant alternative, the two-pointer method.
So efficient for traversing and comparing data.
And so adaptable.
Yeah, we even touched on how to extend it for more complex scenarios.
So the next time you're staring at a tough coding problem,
Don't forget about those trusty two-pointers.
they might just be the missing piece of the puzzle.
And remember, don't be afraid to get creative,
To think outside the box.
to push the boundaries of those algorithms.
That's where the real coding magic happens.
Thanks for joining us on AI.Code.Cast, everyone, and until next time, keep those coding brains buzzing.
See you next time.